Okay, we're going to start off this video podcast with a very intriguing question. I've got two solutions here. This is a 0.2 molar hydrochloric acid solution. It's 150 milliliters. Right next to it, I've got a 0.2 molar hydrofluoric acid solution, 0.2 molar hydrofluoric acid solution, also 150 milliliters. Same volume, same concentration, but this is hydrochloric acid, this is hydrofluoric acid. My question to you is, which one of these two, the hydrochloric acid or the hydrofluoric acid, has the lower pH? Has the lower pH? Now, some of you are going to say, well, why not just place a pH probe into each one? That will solve the problem. No, I want you to use intuition. I want you to think your way through this one. I want you to try to tell me which one, the hydrochloric acid solution, 0.2 molar, or the hydrofluoric acid, 0.2 molar solution, has a lower pH. Well, let's reason our way through this. Hydrochloric acid is a strong acid. That means that it completely deionizes in water. Hydrofluoric acid, on the other hand, is not a strong acid, it's a weak acid. That means that when I've placed the hydrofluoric acid into the water, some of the hydrofluoric acid is deionized, but some of it did not. Some of it did not form hydrogen ions and fluoride ions. Some remain as hydrofluoric acid, or HF. So I can reason then that because more hydrogen ions are available in the hydrochloric acid, 0.2 molar, than the hydrofluoric acid, 0.2 molar, and hydrogen ions are what drive pH, then pH must be lower in this container, in this beaker, than in this beaker. If that was your line of reasoning, you were absolutely correct. But how do we quantify that? How do we do the calculations for that? Well, let's take a look. Well, first let's do kind of a review problem. Let's go back to our hydrochloric acid and ask the question, what is the pH for the hydrochloric acid solution? Well, remember we had a 0.2 molar hydrochloric acid solution, and remember also that when we placed the hydrochloric acid into the water, that there was an immediate and total ionization, that HCl completely, totally turned into the H plus and Cl minus ions that you see here. Now, we don't care about the Cl minus ions, but remember, H plus ion drives pH. That means that because of the fact that HCl, hydrochloric acid, is a strong acid, whatever the initial concentration of the hydrochloric acid was, and we now know it's 0.200, that's also the concentration of the hydrogen ion, 0.200, and the chloride, by the way, again, that I don't care about, but it's there, 0.200 molar, 0.200 molar chloride ion as well. Now, just a point of clarification, students often ask me, well, shouldn't this be 0.1 and this be 0.1? In other words, when this dissociates into H plus and Cl minus, doesn't this 0.200 get cut in half? No, it's a stoichiometric relationship. It's a 1 to 1 to 1, mole to mole to mole relationship. No, this number does not split. Whatever the concentration of this was, and again it's 0.20 molar, is also the concentration of the H plus and the Cl minus. So don't get that confused. All right, so now let's calculate the pH, because remember that pH is determined by the hydrogen ion concentration. Now, we learned in a previous video podcast that the pH was equal to minus the logarithm, that's log, not ln, that's base 10, not base e. pH is equal to minus the logarithm of the hydrogen ion concentration. So let's plug that in. The 0.2 concentration molarity of hydrogen ions then can be plugged in to this position right here. We have minus the log of 0.200. And when we do that in our calculator, we can say minus the log, that's log, not ln, of 0.200 is 0.698. We'll call it 0.70. So the concentration of hydrogen ions then is 0.200, and the pH is 0.70. We've said before that you can have pHs lower than 1. You can have pHs lower than 0. You can have negative pHs. So we're not too uncomfortable with that number, 0.70. It simply indicates we've got a very low pH in this 0.2 molar hydrochloric acid solution. We now know the concentration. It was 0.20 molar H+, but more importantly, we know the pH, 0.70. Now let's take a look at the other solution. This is the hydrofluoric acid solution. Now, remember that for hydrofluoric acid, we are dealing with a weak acid. All right, we're dealing with a weak acid. Hydrofluoric acid does not completely dissociate in water, so we cannot assume that the HF concentration and the H+ concentration is the same. So let's take a look at this problem. We're going to take 0.0100 moles of hydrofluoric acid and dilute it with distilled water to a volume of 500 milliliters. Now we need to understand molarity. Remember that molarity is moles per liter. Not moles per milliliter or millimoles per liter or anything else, it's moles per liter. So we've got 0.0100 moles of hydrofluoric acid divided by 0.5 liters of solution. Well, guess what? That gives us exactly the same concentration as the hydrochloric acid that we used before. So we're going to be able to make a direct comparison of pHs. So we've got now a 0.200 molar hydrofluoric acid solution. Now how do we use that to help us to determine the pH? Well, remember that hydrofluoric acid is a weak acid and therefore is involved in what we call a equilibrium. And that equilibrium involves hydrofluoric acid, of course, but it also involves H+ and F-. I'm going to draw a double arrow just like that to indicate that equilibrium. In order to calculate the pH of a weak acid, I need what is called a Rice table. What does Rice stand for? It stands for reaction, initial concentration, change, and equilibrium. Some people put solution at the very end, and I put it for that reason, but we're going to call it a Rice table. R-I-C-E for reaction, initial concentration, change, and equilibrium. Well, we've already got our reaction. It's the equilibrium between hydrofluoric acid and its component ions, right? H+ and F-. Now let's talk about the initial concentrations. We now know that the initial concentration, that is at the split second, at the exact moment that the hydrofluoric acid was added to the water, that the concentration was 0.20 molar. Now, what was the concentration of H+ and F- in that first initial exposure of the hydrofluoric acid to the water that it was placed into? Well, some of you who are a little bit more astute will say, well, you know what? The water itself had some hydrogen ions in it. In fact, it had a concentration of 1 × 10⁻⁷ molar H+ ions in it to begin with. That's just for pure distilled deionized water. That's true. You're absolutely correct, and that's admirable on your part to remember that. But that's so small in comparison to this number here that we're just going to ignore it. We're just going to say that the hydrogen ion concentration is 0. And the fluoride ion concentration also 0 at initial concentration. That's an initial concentration. But then there's a change. There's a change towards equilibrium. Now let me ask, how much of the 0.20 molar solution was converted to H+ and F-? The answer is, you don't know. You don't know, and I don't know. And when we don't know something in mathematics, we say that we call that value X. Now, I do know this, that in going from an initial concentration to equilibrium, I certainly didn't gain more hydrofluoric acid. I lost some amount, in fact. So I'm going to say that the change is minus X. Minus X is the change from the initial to the equilibrium concentration for hydrofluoric acid. Well, if X was lost here, then X must have been gained here and here. So I'll call those plus X and plus X. So now we're prepared to write expressions for the equilibrium. The equilibrium concentration for hydrofluoric acid is its initial concentration of 0.20 plus its change. So the equilibrium concentration is 0.200 minus X. For hydrogen, it would just be plus X. For fluoride, it would be plus X as well. So I've now got expressions for hydrofluoric acid, H+, and F- at equilibrium. I don't have the actual values, but I'm working in that direction now. I've got the expressions. 0.200 minus X for hydrogen fluoride or hydrofluoric acid plus X for H plus and F minus plus X. Remember, this is the one that's going to help me to determine pH, because if I know my hydrogen ion concentration at equilibrium, it's going to be a snap to figure out what pH. I'll just use pH is equal to minus the log of the hydrogen ion concentration. So where do we go from here? Well, we need a number. We need an equilibrium constant. Now, when we talked about equilibrium before, we talked about a KE. And the KE was the equilibrium constant that helped to determine where the equilibrium lay, to the left or to the right. For acids, we're not going to call it a KE, we're going to call it a Ka for obvious reasons. The A stands for acids. So the Ka then is the relationship in the equilibrium. Remember, HF is dissociating into H plus and F minus, and the Ka tells us where along this line the equilibrium lies. Is it more to this in this direction or more in this direction? So that's a number we're going to have to look up. And I've looked it up, and the Ka for hydrofluoric acid is 6.6 times 10 to the negative 4. 6.6 times 10 to the negative 4. And that's equal to the concentration of H plus. Well, remember that the equilibrium concentration of H plus was X, or plus X, and the equilibrium concentration of F minus was also plus X. So I'll just plug those in, right here and right there. The concentration of H plus is X, the concentration of F minus is X, and the concentration of HF, hydrofluoric acid, at equilibrium, remember, was 0.200 minus X. 0.200 minus X. There we go. Now, I want to show you something, and that is this. It's pretty clear that when I multiply X times X, I get X squared, and then when I pull this up, I'm going to have to multiply this number by this, but then I'm going to have to multiply this by this, and that's going to generate a quadratic equation. Now, I have absolutely nothing against quadratic equations, except they're very time consuming, and if I can avoid using a quadratic, I certainly will. For your purposes, I'm going to do this. I'm going to give you the formula for the quadratic equation. It's X is equal to minus B plus or minus the square root of B squared minus 4AC over 2A. So if you are really gung-ho on doing the quadratic equation, there it is. Have at it. But I'm going to make an assumption that I think is going to be okay, and that is I'm going to assume that this value of X is very small in comparison to this 0.200. I'll check my answer in a little while, but if I determine that that X was less than 10% or less than 1/10 of this 0.200, then I'll accept that inaccuracy. So I'm going to assume that the X here is negligible. This X here is negligible, and I'm just going to ignore it. You know, I'm just going to pretend it doesn't exist. I know my answer is not going to be perfect, but I think it's going to be pretty close to the accurate answer, because I think that because this is a weak acid, that X is not very large. So I'll proceed on that basis. So I have 6.6 and 10 to the minus 4 now equal X times X, or X squared divided by, I'm now ignoring the minus X, 0.200, and I get this. I'll pull the 0.200 up algebraically, and I get 6.6 times 10 to the negative 4 times 0.200 equal to X times X, or X squared. When I solve for X, I get this number, 0.0115. Well, guess what, folks? X is the hydrogen ion concentration. That's what I was looking for. X is the hydrogen ion concentration, and now I can determine the pH. Before I do that, though, I want you to notice that, remember, 1/10 of 0.200 would have been 0.02. This is 0.0115. That's less than 10%. I was okay in my assumption of allowing that X simply to disappear, okay? So you have to check that, but on the other hand, it's a lot easier if you just ignore it. If you feel that that X is sufficiently small, you can just ignore it. But again, this is the quadratic equation. If you want to use that, you certainly can. All right, so now let's figure out the pH. How do we do that? Well, the pH is equal to minus that log, that's log, of the hydrogen ion concentration, which is 0.0115. So 0.0115. And I get this number, 1.94 approximately. 1.94 then is my pH. That's the pH of this container, the 0.2 molar hydrofluoric acid solution. Well, let's look at what we've just done in our calculations. We've confirmed our original intuition. Remember that we said in our original intuition that we felt that the hydrochloric acid would have a lower pH since it was a strong acid, and the hydrofluoric acid of the same concentration would have a higher pH. Since it's not a strong acid, well, look what happened. In our review problem, we started with a strong acid that had a concentration of 0.2 molar. We calculated the pH, and it was 0.70. Now in this problem, we use a weak acid of exactly the same concentration. We calculate 1.94. That makes perfect sense. For a given concentration, a weak acid will have a higher pH than a strong acid. I'll see you on the next video podcast.